Thank you, Marcus. Well, as Marcus said, this is the third presentation in the educational series, and the second one about SPECT reconstruction. Now we will take a bit deeper look into technical and mathematical details behind the reconstruction algorithms. And as Marcus said, please type in the questions that you have into the chat box, and we will try to answer them when the presentation ends. And this presentation will be recorded, and we can send the link out on request. All right, but the overview for this presentation is as follows. I will start with the basics of iterative reconstruction, and after that we will dig deeper into MLEM and OSEM and try to figure out what those mean, and then we'll talk quite a lot about compensation methods, how to handle scatter, attenuation, and the collimator effects in iterative reconstruction. And after that, we will talk about Bayesian or penalized likelihood reconstruction, and end up with some comments how you can calibrate your reconstructed images into quantitative images so that you can present the voxel values in becquerel per milliliter and so on. But let's start with the basics of iterative reconstruction. There are a lot of people who are working in the field of iterative reconstruction who don't like the term iterative at all. They like to use the term statistical. They like to call these methods as statistical reconstruction methods because the noise is implicitly modeled in the reconstruction algorithms. But I will probably mix both iterative and statistical terms in when I talk. So bear with me. They mean the same thing. As many of you know, the filtered back projection used to be the reconstruction method of choice maybe 10 or 15 years ago, but it has now been pretty much completely replaced by statistical reconstruction methods in SPECT and in PET. And the reason for this is that the FBB works quite poorly with noisy data because it assumes that the projection data is noiseless, which is not really the fact in SPECT, but we have a lot of noise in our projection measurements. The FBB also works poorly with attenuated projection data because it assumes that the projection data is perfect, and it's I don't like to say impossible anymore, but at least it's quite difficult to add non-uniform attenuation correction in the FBB algorithm. I know that there are some papers out there, but it hasn't been really utilized in clinical environment. Also, the collimator effects are quite difficult to model in FBB, and the same goes with scatter. It's very difficult to add the compensation for it in the FBB algorithm. Of course, you can do the corrections pre-reconstruction or post-reconstruction, but still the results are usually not as good as with statistical algorithms. Fortunately, the dimensions of the matrix sizes and the number of projections is very low in SPECT and PET when you compare, for example, to CT, where we use 512 by 512 matrix sizes, and we have several hundred slices. In SPECT and PET, the dimensions are much smaller, and even though the statistical reconstruction methods they are computationally very heavy, but due to the small dimensions, we still can reconstruct the images in clinically acceptable times. And this has been the clinical situation for years now. But if you compare it to CT, at least the model-based reconstruction methods, they are not as widely used as the statistical reconstruction methods are being used in SPECT and PET. But if we take a look on the statistical reconstruction methods, we can say that the algorithms, they usually consist of 4 different parts. We have the image model, then we have the system matrix, or we can call it the projector, and then we have the cost function, and followed by the optimization algorithm. And if we take a look of the image model simply states how the image is presented, and probably in 99% of the cases we present our image using pixels or voxels. That is the most common choice. But we can present the images also using Kaiser-Bessel functions, which are these blobs shown in here, or we can also use kernels. We don't talk about the kernels or the Kaiser-Bessel functions during this presentation, but we assume that the image is presented using pixels or voxels. But you should know that there are the other choices available too. One other thing that we, when we talk about the image model, we have to consider is the prior assumptions about the activity distribution. And usually we assume that the neighboring voxels, they are not correlated, their noise is not correlated, but there can be correlations between them, and that is something that we will come back in the Bayesian or the penalized likelihood section of this presentation. But for now, we assume that our image is presented by voxels, and there are no prior assumptions about the activity distribution that we are reconstructing. Then the next ingredient of a statistical reconstruction method is the system matrix, and this is probably the most important part of an iterative method, and it tells you how we convert the 3D image into 2D projections and back, how we convert the projections into images. Because as you know, the imaging target, it's usually a 3D object, and our measurements are in 2D. So we need some kind of mapping between the 2D projections and the 3D image. And the system matrix is the mapping. What the system matrix, what the elements tells us is the contribution that the image voxel J has on the image pixel I. So what is the probability that the photon emitted in here will be detected in a projection pixel in here? And if we want our image to be the best possible, we should include all the factors that affect the image formation. We should include them all in the system matrix. So attenuation, collimator and detector effects, and photon scatter should be included in the projector. And we will come back to this when we talk about the compensation methods. The third part of statistical reconstruction method is the cost function, and this is the function with which we compare the projections that we calculated using the system matrix to the measured ones. So this is some kind of function that measures how well they match, and if there is a perfect match, then we know that our reconstructed image is ready. And there are many different type of cost functions available. You can use likelihood, squared difference, posterior distribution, and so on. And the fourth and the last ingredient of a statistical reconstruction method is the optimization algorithm. and this is the method with which you maximize or minimize your cost function. And there are different algorithms available: expectation maximization, gradient descent. And the algorithm that you can use, it is usually bound to the cost function that you are using. It's sometimes difficult to use certain optimization algorithms with certain cost functions, but usually these are somehow linked together. And these optimization algorithms, they are usually iterative methods where you update the estimate that you got from a previous iteration, and you update that and go on with the iterations. And if we try to present this in a nutshell, how the statistical reconstruction methods work. So in here we have an image. Let's say that we got this in the during the first 2 iterations of our statistical reconstruction method. So the first step is to apply the system matrix to the current image, so that we could check how good this estimate really is. And by applying the system matrix to the image, we will get calculated projections, which are shown here. We have the anterior projection here, lateral, and posterior in here. And then you have the measured projections. And then you compare the calculated projections to the measured ones according to your cost function. And if the cost function hasn't received or hasn't gained its minimum or maximum value, you will continue with your optimization algorithm and update the current image, and then you iterate another round, and you will continue this as long as it takes for the cost function to gain its maximum or minimum value, or quite often you just terminate the iterations after a couple of iterations, because otherwise it will take too long to wait until the algorithm is fully converged. Then the next section is about MLEM and OSEM, which are the most common reconstruction methods in SPECT and also in PET. And let's take a look of these. Because I'm a physicist, I have to show you a couple of equations, but bear with me. So as many of you know that in SPECT imaging, the projection pixel values, they are Poisson distributed. So the probability that we get C number of counts in some pixel when the mean of the counts or the expected number of counts equals R is this guy in here. Then we can assume that each projection pixel value is independent of all the other projection pixel values, and thus we can multiply these individual pixel probabilities, and then we end up with the likelihood function, which looks like this. So it's just these guys multiplied together, and we have replaced the expected number of counts by the number of counts that our projector, our system matrix, will give us, and that's pretty much it. And when we maximize this likelihood function using the expectation maximization algorithm, we will get this kind of update equation, which by the first glance it looks horrible. There are a lot of sum signs and indexes and so on. But if we take a closer look of this and we look at the denominator first, we can see that this is the projection of our current image. So we have applied the system matrix to our image. Then we divide the measured projections with the calculated ones. So we are comparing the measured and calculated projections. And if the division gives us just ones, just number ones, we know that the projections, the calculated projections, they match the measured ones perfectly, and we can terminate our algorithm. If they don't match, we can calculate by updating the image using this guy in here. So it works in the same way as I explained the statistical algorithms. We apply the system matrix in here, then we compare the calculated and measured projections and update the image, and we run this loop as many times as we have to do. And the cool thing about the LMEM algorithm is it takes the Poisson noise, the distribution of the counts implicitly into account. The LMEM algorithm, it's usually, even in these days when we have very fast computers, it's considered to be too slow, and therefore this OSEM algorithm, ordered subsets expectation maximization algorithm, has been developed. The OSEM, it works in the same way as MLEM, but it uses only a subset of projections to update the image. So it's faster than MLEM. And in this case in here, we have 8 projections total. And each MLEM update would use all these 8 projections. But in OSEM, in this case, we have split the projections into 2 subsets. So we have a subset number 1 is these black projections, and subset number 2 is these white ones. And we first use the MLEM algorithm using the black projections, calculate an image, and continue with the white ones. So at the same time, when we use the all 8 projections, we have in fact updated the image 2 times. The MLEM and OSEM, they don't exactly give you the same image, but still they are so close to each other that the OSEM has been widely accepted, and it's the most well-known and most well-used reconstruction algorithms in both SPECT and PET. And the OSEM algorithm, it was developed by an accident by Richard Larkin, and he was implementing the MLEM algorithm, but he made a coding mistake, and then he noticed that his coding mistake made MLEM much faster, and that was how the OSEM was born, maybe 20 or 25 years ago. But now it's the most common reconstruction method in SPECT. So now we have talked about the basics of statistical reconstruction. We know how MLEM and OSEM works, and now we will take a deeper look on the compensation methods. And usually the system matrix, it's considered as the most important ingredient of a statistical reconstruction method. And as you know, the SPECT imaging, it is hampered by attenuation, collimator and detector effects, and scatter. And in order to correct these effects, we need to model all of them in our system matrix. And in order to be quantitative, we have to make the activity distribution independent of the voxel position in the image. And for that, we need to compensate all these effects. And I'm talking about compensation, not correction, because we are not really doing any post-reconstruction correction, but we are modeling these attenuation, collimator, and scattering effects in our system matrix. So if we take a look of this image in here, we have our activity distribution in here, and then we have our attenuation distribution in here. And now if we make projections of this, we assume that the detector plane is on top of the patient in here. So instead of just summing the values along these projection rays, we are calculating how much the photons, when they propagate through the body, how much they attenuate. And we get the attenuation values from the attenuation map in here. And nowadays, because we have these hybrid scanners where we have combined gamma camera and CT, we can get the attenuation maps quite easily. But attenuation can simply be modeled using this exponential equation for the attenuation, and we just check how the photons, how they attenuate when we form the projections. And if we don't do the attenuation compensation, our reconstruction algorithm, it cannot know that the lung density is different than the soft tissue density, but it assumes that because there is more activity coming from the lung area, it assumes that okay, there has to be more activity in the lung area. But when we model the attenuation, our reconstruction algorithm knows that okay, there is lower attenuation in here, and I will put less activity in there because it's the difference in the projection counts. It's due to the different attenuation factors. The next compensation is the collimator and detector response compensation. This was the same image that Helen showed in her previous presentation, but you know that the further we go from the gamma camera detector, the bigger our point bed function will get, and this is mainly due to the collimator. The gamma camera, it also has an intrinsic resolution of a couple of millimeters, but because the collimator resolution it is measured in centimeters, this intrinsic resolution has relatively small impact on the size and shape of the eventual point spread function. And we can easily, or quite easily, model the effects of the point spread function using a two-dimensional Gaussian function. So instead of projecting a point source as a point, we will project it as a Gaussian function whose full width at half maximum depends on the distance we are from the detector plane, and it has quite a big impact on the gamma camera images. Here you can see DAT scan images reconstructed with attenuation correction only, and here you can see images which have been reconstructed with the Gaussian function based collimator model, and you can see that the resolution in here is much better. The Gaussian function, it works quite well for low energy isotopes, but for isotopes which emit high energy photons, the 2D Gaussian model, it is not enough because it doesn't include collimator scatter, septal penetration, and so on. And so the point spread function with the high energy isotopes, it doesn't look like a Gaussian function anymore. It has this star shaped, and also the full width at 10th maximum, it's much bigger than the Gaussian model would assume. So what Hermes has done, we have generated a huge amount of point spread function tables using Monte Carlo method. So we simulate not only the geometrically collimated photons, but we also simulate the effect of the collimator scatter, the LED X-ray emission, and the collimator penetration. And we just put point sources at different energies in front of the collimator, run Monte Carlo simulation, and save the tables, and then use those tables inside our reconstruction algorithms instead of the 2D Gaussian model. Our Monte Carlo simulator, it's developed in-house. It assumes that the collimator is made of lead. It's characterized by its hole length, hole diameter, and septal thickness. And then behind the collimator, we have the detector crystal, which is characterized by its crystal thickness, intrinsic resolution, and energy resolution. We also model the back compartment because it's possible that the high energy photons that they pass through the crystal but backscatter from the back compartment, and we also model that in our Monte Carlo simulations. We have done quite a lot of validation work in order to check that this method works. We have tested it with different energies compared with the published results, and it seems to work quite well. We have also done real physical measurements, compared the iodine 1, 2, 3 spectrum, the measured spectrum against the simulated spectrum, compared points with functions with different isotopes. Here you have results with the iodine 131. And we have done a bunch of phantom work to check that the algorithm really works. So what it does for the images is that it increases the recovery coefficients. So here we have the NEMA IAC phantom, which has these spheres of different diameter, and if you compare the recovery coefficients, which are the ratio of the calculated and measured activity inside the sphere, you see that the full model, it provides you much more accurate recovery coefficients than the Gaussian model. And this was with iodine 1, 2, 3. With yttrium, if you compare the Gaussian model and the Monte Carlo model, you see that there is much less background activity. In this case, there was activity only in the spheres, and the background was cold. But because you cannot model the points with functions accurately with the Gaussian model, you will get also activity in the erroneous activity in the background, which is completely missing in the Monte Carlo reconstructed image. And also, if you look at the DAT scan images, the profile through the striatum, which has much higher peaks and deeper valleys with the full model than with the Gaussian model, and that of course indicates that the contrast is better with the full model. And even though Markus said that this is an educational series, but I still have to advertise a bit that the Hermes is the only company at the moment who is doing the full Monte Carlo modeling of the collimators. The last but not least compensation is the scatter, and this is probably the most challenging one. For attenuation, we know that the photons attenuate according to the exponential law, and for the collimator point rate function, we can use quite often the 2D Gaussian model, but it's really difficult to generate some kind of mathematical scatter point rate functions. And due to those problems, Hermes has selected the approach to use Monte Carlo modeling of the scatter. So when we calculate the projections, we follow the path of the scattered photons according to our Monte Carlo algorithm. And at every interaction site, we project the scattered photons towards the detector according to the convolution-based force detection principle. And that is how we get the scatter contribution on our projected images. The scattering, it usually creates some kind of hazy background around the images. And here you can see cardiac images reconstructed without scatter correction. These are technetium images, and you can see that the contrast between the ventricle and the myocardium is better with the scatter corrected images. The same thing with the bone images. With the scatter modeling, without scatter modeling, there is activity in the soft tissue that you can see, but it is much less pronounced in the scatter compensated images. And the same thing with the DAT scan images. You can see that there is quite a lot of scatter around the striatum. that is quite nicely removed from the scatter corrected images. All right, now we have talked about the basics of statistical reconstruction, MLEM, OSEM, and the compensation methods, and we will take a short look on the Bayesian reconstruction methods. So you might ask, why do we need a new family of reconstruction methods? What is the problem with the MLEM or OSEM algorithm? And the problem with this is that even though you model the noise in the projection level, you don't really model it on the image level. So you don't consider, for example, the correlation between the neighboring voxels. You just assume that voxel I is no way correlated to a voxel J. And what this does, it leads to a situation that the reconstruction, it is a fit to a noisy data, and these voxel values are our fitting coefficients, and they are deterministic values. They are not some measurement of a probability function or anything. They are just deterministic fitting coefficients. And when you fit something to a noisy data, you will easily get noisy fit. And how we can fix this? One method is to add some kind of penalty into the reconstruction algorithm based on the local voxel value differences. We can, for example, assume that the voxel value I, its value should be similar to a voxel value J, because how the noise appears in NM images is it appears as noise spikes. So very high individual voxel values or very low individual voxel values when you compare to the neighbors. But the problem with this approach, for example, in this case, where we have a bone image, is that the voxel values I and J, they really should be different, because the voxel I is in bone and J that is in soft tissue. But what we can do is that we can use the CT image to guide our penalty. We can use the CT image to tell our penalty algorithm that, okay, in this case, I and J, they belong to a different tissue class, but we shouldn't assume that their voxel values should be similar. But if we would have a voxel in here, then these voxel values, they belong to the same tissue class, and then they should be similar. And the penalized statistical reconstruction algorithms, they work in a very similar way as the normal statistical reconstruction methods. We project the image based on our system matrix. We compare these calculated projections to the measured ones and calculate the update factors based on the fitting. But in addition to the fitting update factors, we also take into consideration the penalty factors that we calculate based on the image. And then we take a quick look what kind of images we can get with the penalized or Bayesian reconstruction methods. In here we have the JSAC phantom images reconstructed with OSEM, RDP, relative difference prior, which is similar to the GE's Q-clear PET reconstruction method, and then an anatomical prior where you use the CT image to guide the penalty factors. And if you compare these, of course, you see that these anatomically guided images, they look much better than OSEM or RDP. Same thing with the bone studies. Okay, if you compare RDP with the OSEM, you see that, okay, there is maybe a bit less noise in the images, and if you check the SUVs, they are somewhat higher with the RDP than with OSEM. But when you utilize the CT information in here, you get some kind of hybrid looking images. that are look a bit like some morphosis of CT and SPECT images. But all these methods, they are available in the hybrid recon package. So if you have time, please check them out and see what you think. All right, the last section about calibration. As I said before, the purpose of a high-quality reconstruction algorithm is to produce images whose voxel values are independent of voxel location, because then we can use a single conversion factor that converts our voxel values, the counts, to our activity concentration in the voxel. We can do the calibration using the cylinder source. We just put the known amount of activity in a cylinder, image it, check how many counts are emitted, and then we just calculate the ratio between counts and the known amount of activity, and that is our calibration factor. We can do the same thing with the point source. The cylinder source and point source, they are both supported by hybrid recon. You can also use planar calibration phantoms, and if we would use the Monte Carlo based reconstruction method, we could get rid of the calibration process completely and use the Monte Carlo to model and produce absolutely quantifiable images directly. But the MERD pamphlet number 23, it recommends to use the cylinder calibration source, because that will fix some of the issues that we might have with the reconstruction algorithms, and that is also what Hermes at the moment recommends. So use the cylinder calibration phantom. There are publications out there which compare the different calibration factors. This is from the Michigan group, where they compare different calibration factors for IODA 131. And for example, if we check the high energy collimator values, the calibration factor values, we see that they range from 7.5 counts per second per megabecquerel to 32.9 with the uniform tank. So there is a huge variation in the calibration factors. So please be careful and use the method that Hermes recommends, that usually leads to the best results with hybrid recon. So in summary, we have discussed about the ingredients of statistical reconstruction. We took quite a deep look how the compensation methods, how they work. We talk about MLEM and OSEM, about Bayesian reconstruction, which might be the next big thing in the reconstruction work, and some practical results of calibration work. This ends my presentation. I thank you for your attention, and we can start to take the questions from the chat. Thank you.
Thank you so much, Antti. That was really interesting. I had no idea that OSEM was just a coding mistake, in fact. That's a really good fact.
Yeah, that's quite surprising. Yes.
Yeah. And I agree with you that it looks like from those images that you showed that the Bayesian anatomical prior should be the next big thing. Those images looked awesome. So it would be really good to get some more research into that and some more clinical demonstration of how useful that can be.
Yes.
Okay, I'm looking at the questions window. Okay, we have a question here. So first question, will the slides be available? The recording will be made available afterwards. If you email us, then we can provide a link to that recording for you. The next question, this is from Matthew Walker. Very nice presentation, thank you. You mentioned that the detector is part of the Monte Carlo model. Does Hermes support the latest CZT detectors or only the older NAI ones?
at the moment only sodium iodine, but there is some research work going on the CCT side also. But let's see what happens in the future.
Okay, great, thank you. That's it for the questions at the moment. Just hang on for a little longer and see if anyone's got anything exciting brewing. Okay, not seeing anything more. Perhaps we can.
I apologize. This is Andrew. One of the others. I can't because I can't type a question because I'm an organizer. So, Auntie, I would just ask, how much faith do you have in the newer method with the bias from the CT as being realistic reconstruction, or is it has it gone too far in waiting? Do you have a feeling for that? I know time will show, but in a realistic human setting.
Yeah, I think it depends on the application. At the moment, we are preparing a paper where we have used the anatomical reconstruction in bone SPECT CT, and there it seems to work quite well. But it's of course the anatomical and the emission methods. They should have at least some kind of correspondence. The anatomical reconstruction methods, they are, at least in the research community, they are quite a big research topic in PET MRI, in brain PET MRI, where the MRI and the, for example, the FDG PET image, where they look similar, at least to some extent. So I think that the bone SPECT CT is one good candidate for the anatomical prior information, and of course there are also, well, there are not SPECT MRI scanners available, but there are people who are doing these ictal and interictal brain SPECT and MRI studies, and that might be one case where the anatomical information from MRI might be helpful.
Okay, we have a few more questions. So this is from William Irwin. The resolution of the recon with the CT-weighted penalization appears much better. What accounts for the resolution improvement?
Well, how the resolution improvement, how it's generated, is that the algorithm will force the activity. For example, in the bone case, it forces the activity to be inside the bone, and that will of course increase the resolution of the SPECT images quite dramatically. But as I said, it probably cannot be used in all occasions, because there has to be some correspondence between the SPECT uptake and how the CT image looks.
Great, thank you. Another question. This is from Yasser Shikari. I'm sorry for the pronunciation there. Thank you so much for this very good knowledge. Please, I have one question about how the dose for pediatric patients scales. How much should I inject, for example, pediatric patient of 3 to 5 years to work with the reconstruction method? I mean, in the UK, we've got a, I think it's IPEM possibly, or RSAC, the people who give licenses for injection of radiopharmaceuticals, have a schedule for how much you can inject based on the weight of the patient. I don't know if it's the same in Finland.
Yeah, we use the EANM dose.
Yeah, the EANM one, of course. Yeah, thank you.
Yeah, but otherwise it's a bit difficult to give advice. I would use the EANM calculator and use that to decide the pediatric doses. We have done research work where we compared the full and half dose imaging. This was in adults and in cardiac SPECT, and we noticed that the hybrid recon it can handle the much noisier data well, and we get better quality images with the half dose when compared to the full dose and standard reconstruction method. But for pediatric patients, we haven't done any research work.
Great, thank you. So we have now from S. Peter Kim. Hello, thank you for the presentation. I have looked at the different Hermes software options for reconstruction. Is there a place where we can get an in-depth explanation for each reconstruction technique provided by Hermes?
Yeah, I think that for that we have to organize some kind of private demonstration how the
yeah, that might be the best thing. Or we have the white paper that you wrote, Antti, which is quite informative on that, and a number of publications from Antti's research groups in Finland give some detail on these things. So that's probably the best thing to do. So if you follow up on the Hermes Medical education address, we can send you that white paper. That's probably the best place to start.
Yep.
Okay, another question from William Irwin. What sort of post-filtering, if any, are applied?
For the Bayesian reconstruction, the basic idea is that the algorithm itself, it handles the noise, so no post-filtering is needed. But for OSEM hybrid recon, we have the three-dimensional Gaussian filtering available, and then we have the frequency space filter, well, the Butterworth filter available. But I would recommend probably to use the three-dimensional Gaussian filter that will give you results that are well, maybe a bit better than with the frequency-based filters.
Thank you. So this is a question from, I apologize for pronunciation here, Yanis Argyridis, I think. Interesting seminar. This might sound far-fetched, but are you aware of machine learning algorithms for reconstruction? Do you think statistical methods will continue to offer better image quality compared to ML?
Yeah, that is a really good question. I know that there are algorithms that where you just give the machine learning or deep learning network just the projection data, and it will give you the reconstructed image as an output. Maybe that is one of the goals, but that is still probably not the clinical reality, not just yet, because there are always can be cases where you don't have any teaching material available for your deep learning network. But I know that for example, people have combined the statistical reconstruction methods and the deep learning networks for noise reduction pretty much in the same way as the Bayesian methods do, but those are not yet clinically available.
Interesting. Okay, and now we have another question. This is from Martin Tornai. To which collimators do the algorithms and corrections apply? Pinhole, cone beam, fan beam, etc.
At the moment, we support the parallel hole and fan beam, but at the moment we don't support pinhole and cone beam.
Okay, great, thank you. Right, I think we've got to the end of the, oh, sorry, there's more questions just come through. I spoke too soon. Okay, this is a question from Sarah Williams. For the anatomical prior reconstruction, which looked great, thank you, there would be a huge increase in the number of SPECT CTs we perform, especially whole body SPECT CT. What procedure is this aiming to improve? Will it have a niche? It may be hard for us to justify a whole body SPECT CT as they do routinely in PET CT.
Yeah, for example, the hospital where I work, we have done whole body, well, 3-bed bone SPECT CT studies, quantitative, for I think that for 4 or 5 years already. We don't do planar studies anymore because with Hermes you can reproject the SPECT data into planar studies. So we have moved completely from the planar bone imaging to a whole body SPECT CT bone imaging, and that is probably the next step we are going to take, is that we are going to test out the anatomical reconstruction in bone SPECT CT. But I know that it's a big step to take. But now, for example, if we have a CT that is broken in our gamma camera, and the NM doctors, if they have to take a look of the normal planar whole body bone scans, they say that there is not enough information to make a report about that, because the CT and the SPECT, it will give you so much information, and the SUVs, they are so good in scaling the images in the same way, and also in the pre and post imaging, where you can compare the voxel values and the uptakes in lesion suspicious areas and so on. It's a big improvement.
That's really interesting. It's one of those things that you have to sort of push it to get it started, but once it's started, you can't imagine life without it.
Yeah, that's true.
Yeah, one of those tricky clinical scenarios. Okay, great. This is a question from Layla Unali. Apologies again for pronunciation of that name. Thanks for the excellent presentation. My first question is related to the recovery coefficients. If we calculate doses for organs at risk with big sizes, kidneys or liver, it is important to fix the recovery coefficient, like the case for small lesions. I think she's asking, is it possible to apply a recovery coefficient to the reconstruction there?
In hybrid recon at the moment, no. I think that is something that we probably should include in our dosimetry algorithms, and for voxel dosimetry, it's a bit tricky to do. So it would be in the organ-based dosimetry package, where
yes,
that kind of correction should be available.
That's right. That's actually already in the organ dosimetry package, but that relies on, because it relies on having drawn your region first, then it knows the volume. Yeah. And so if you've got a scaling that you know volume to recovery coefficient, then it can apply it then. It's a bit more of a tricky question to know how to apply that just to reconstruction without any regions drawn yet. But yeah, it's an important question and an important thing to consider when doing dosimetry for sure. Okay, we have a second question from Layla. What is the influence of the calibration factor on the calculated dose? As I understand, the calibration factor for high energy, I think, or for HE, is from 7.5 to 32.9.
Yeah, it has a huge effect. Of course, the dose will pretty much scale linearly with the activity. If there is a beta emitter accounted, and it has a huge effect on the dose. So for dosimetry, the calibration factor, it really has to be correct.
I think that Layla might have got those factors from the slide that you showed.
Okay.
With the work done. In the Michigan site, I think, where they looked at using different numbers of voxels to make the calibration. And it was, I think your slide there was just demonstrating how much effect that can have if you don't go with the recommended cylinder method. So that's what we would say is to go with the cylinder, which was it's just the last column or uniform tank in this case. Yeah,
of course this doesn't show the doses, but the effect on the quantitation, it's really big.
Great. I think I cannot see any more questions. Just hanging on for a little longer. I think we might be there. Yeah, let's call it here. Thank you so much, Antti, for that really interesting presentation.
Yeah.
And thanks everybody for coming along to listen. And goodbye.